Hi, my name is Shafi Mama Roslan, and I'm going to present biodiesel from waste cooking oil. What is biodiesel? Biodiesel is made from oil mixed with alcohol to form fatty acid alkyl esters. It is generated through trans-esterification process. It is a renewable energy source known for its reliability, efficiency, and availability, reducing harmful effects caused by non-renewable fuel. Biodiesel is eco-friendly, biodegradable, and emits fewer pollutants, making it a great alternative fuel for diesel engine. Fun fact: biodiesel is a drop-in fuel, which means it's compatible with existing diesel engine and distribution infrastructure. However, because most engines cannot run on pure biodiesel without any proper modification, it is usually blended with petrol less than 10%.
Greening fuel. As diesel resources become diminished, it is important to find ways to make energy that are better for the environment. Factors such as increased global demand, geopolitical instability in oil-producing regions, and finite fossil fuel reserves contribute to the diminishing availability of diesel resources. One way is by recycling things we have already used, like waste cooking oil, and turning it into a new kind of fuel called biodiesel. This biodiesel is renewable, which means we can make more of it without running out. By doing this, we can help reduce waste and make energy greener and more sustainable way. How biodiesel can be produced from waste cooking oil? Producing biodiesel from waste cooking oil involves a chemical process called trans-esterification. This method transforms the triglyceride present in the oil into biodiesel. In this process, waste cooking oil acts as the ester, which is mixed with the methyl alcohol or methanol. To initiate the chemical reaction, a catalyst is added to the mixture. The result is the formation of methyl ester known as biodiesel, with glycerin as a byproduct. Once the trans-esterification process and the treatment of crude biodiesel are complete, the biodiesel are ready for use. Preparation of biodiesel. There are three materials needed in this project, which is first, waste cooking oil, second, sodium hydroxide pellet, and lastly, methanol. Preparation of biodiesel consists of four major steps, which is step 1 is pre-treatment of waste cooking oil. The waste cooking oil was filtered through the quantitative filter method to remove the suspended solid particle. After filtration, the waste is then heated on a magnetic stirrer and hot plate with constant stirring for 30 minutes to eliminate any particles that present in the waste cooking oil. The next step is the preparation of the catalyst solution. The catalyst, which is sodium hydroxide in pellet form for this project, is breaked and ground into the powdered form using a mortar and pestle to increase the surface area, hence increase the rate of solubility. And then methanol was measured in a beaker, and the sodium hydroxide is added into the beaker with low heat and constant stirring until it's completely dissolved. The mixture of methanol and sodium hydroxide is left to cool to room temperature. Third step for trans-esterification process. The treated oil is then heated to the selected temperature, which is in this project 50 degrees, 60 degrees, 70 degrees on a hot plate with a constant stirring. The temperature of waste cooking oil is constantly monitored using laboratory thermometer. When the oil has reached the selected temperature, the mixture of ethanol and catalyst will added. The heater is immediately turned off with continuous stirring for 45 minutes. After that, the mixture was left at room temperature for 24 hours to allow all oil to react with the methanol and to allow all the glycerin form to sediment at the bottom of the beaker to ease the separation. Step 4. Treatment of crude biodiesel. After 24 hours, the crude biodiesel is then filtered by using filter paper to separate the biodiesel and glycerin. After the filtration process completes, the biodiesel then placed in a hot water. Methodology for chemical properties analysis. Functional group or chemical properties in the synthesis were determined through a line FTIR model spectroscopy. The infrared spectra was recorded by passing a beam of light through the sample within the 4,000 to 400 cm range. Following this, the identified functional groups were analyzed and compared to those present in commercial diesel. A methodology for physical properties analysis. There are two physical properties in this project, which is density of the biodiesel and viscosity of biodiesel. For biodiesel density calculation, it is calculated using a capillary relative density bottle of 50 ml in volume. The equation is like this, where density is equal to the weight of biodiesel divided by the weight of distilled water times density of water. Next, biodiesel viscosity calculation. There are two types of viscosity, with dynamic and kinematic viscosity. The method used to measure the dynamic viscosity of biodiesel converted from waste cooking oil use the same concept as the falling sphere viscometer. The equation for the dynamic and kinematic viscosity are like this. Result and discussion for FTIR analysis of varying temperature of biodiesel. Figure X displays the FTIR spectrum of biodiesel synthesis from waste cooking oil at varying temperatures from 50 to 70 degrees Celsius in comparison to commercial diesel.
In all biodiesel samples, a prominent signal was observed at 1741 wave number and 1357 to 1174 wave number, indicative to C double bond O and C bond O bonding respectively. Both signals were associated with ester compounds, which are the primary functional group in biodiesel. Notably, both characteristic peaks were absent in commercial diesel spectrum, emphasizing the dissimilarity chemical characteristic between biodiesel and commercial diesel. Additionally, peak at 2980 to 2855 wave number and 1454 to 1446 wave number appear in both biodiesel and commercial diesel spectra, reflecting long-chain alkyl and methyl groups CH3 respectively. This commonality suggests the presence of similar molecular structure in both fuels, as both sources are categorized as hydrocarbon. However, large peak in diesel spectrum at wave number 2918 to 2855 wave number designated strong CH2 stretching responsible for higher carbon content in commercial diesel. This result suggests that the esterification reaction temperature in the range of 50 to 70 degrees did not significantly impact the functional groups in all three biodiesel samples. At this temperature, esterification is still occurring, but higher temperature will result in the higher yield and increased rate of reaction. Result and discussion for physical properties analysis. The result and discussion of this slide focus on analyzing the physical properties and biodiesel under different temperature conditions, with a particular emphasis on density and viscosity. At the left side is the table for density calculation, while the right side is the table for viscosity. The density result reveal integrating pattern. At 50 degrees Celsius, the biodiesel exhibit a density of 876 grams per centimeter cube, which marginally decreased to 875 grams per centimeter cube at 60 degrees Celsius, and slightly increased to 877 grams per centimeter cube at 70 degrees Celsius. Comparatively, commercial diesel demonstrate a density of 853 grams per centimeter cube. This data showcase the influence of temperature on biodiesel density, with minor fluctuation observed across the temperature range. Notably, despite this variation, biodiesel's density remains relatively close to that of commercial diesel, especially at higher temperature. Dynamic viscosity measurement reveal a nuanced trend, with viscosity value of 1.14 pascal second at 50 degrees Celsius, 1.02 at 60 degrees Celsius, and 1.26 at 70 degrees Celsius compared to commercial diesel's viscosity of 1.63. This data highlights the temperature sensitivity of biodiesel viscosity, with viscosity decreasing initially and then increasing at higher temperature. Similarly, kinematic viscosity value exhibit a similar pattern, with value of 0.001 at 50 degrees Celsius and 0.001 at 60 degrees Celsius and 0.001 at 70 degrees Celsius. Contrast with commercial diesel's kinematic viscosity of 0.002. Contribution to society. First, environmental benefit. By recycling waste cooking oil into biodiesel, we can reduce the amount of waste going to the landfill or being improperly disposed of, mitigating environment pollutant and minimizing negative impact of ecosystem. Next, job creation and economic growth. Biodiesel production from waste cooking oil can create employment opportunities in various sectors, including collection, processing, and manufacturing, stimulating economic growth and contributing to local and national economies. And lastly, it is a renewable energy sources. Biodiesel derived from waste cooking oil provide a renewable alternative to conventional diesel fuel, reducing reliance on finite fossil fuel resources and decreasing greenhouse gas emission, thus contributing to effort to combat climate change. Here's some achievement from this project, which is publication, intellectual properties, and research grant.